the RC operational amplifier circuit. So this is the extension, yeah, of the op-amp chapter that we have learned in the semester 1. Please review again if you forgot the slide, as well as the chapter maybe on operational amplifier. Yeah, here we use the ideal op-amp approximation. What is ideal op-amp approximation? In ideal op-amp, the output impedance here is 0, input impedance here is infinity, and the gain is also infinity. If input impedance is infinity, so basically V plus equals to V minus. V plus equals to V minus, and there is no current. I plus equals to I minus equals to 0. Okay, this is the ideal op-amp approximation. So if you forgot about this, please refer back to the semester 1 discussion on this. Yeah. Because we are going to use this ideal op-amp approximation throughout this chapter. So in this case, R0 is 0, V output will be the gain times the V plus minus V minus. If the gain is infinity, it means that V plus is basically equals to V minus. So if the input impedance is infinity, yeah, Ri is infinity, so I plus equals to I minus equals to 0. No current enters the op-amp because of the infinite input impedance. Okay. Yeah. And because if V plus equals to V minus, E plus equals to V minus, I plus equals to I minus equals to 0. Okay, please remember this principle of ideal op-amp. So let's now try to solve an op-amp circuit that has a capacitor in it. Yeah. So for example, here the capacitor is connected from the output into the inverting input. Inverting input is the negative port of the negative input port of the op-amp terminal, and then that negative inverting input is also connected to R1, which is then connected to the voltage 1. Then the non-inverting input is connected to ground. So from here, looking from here, you what can we see that I minus should be equal to I plus should be equal to 0, right? And here V minus should be equals to V plus. And since V plus is connected to ground, so this is equals to 0. So the volt potential here is 0 volt. This is also 0 volt. Okay, so here you can use Kirchhoff Current Law to solve this circuit. Okay, V plus equals to 0, and you use, and there is no current. Also, I minus equals to 0. Here you consider all the currents entering into this node. Okay, so using Kirchhoff Current Law, V minus or sorry, it goes like this. Yeah, V1 minus V minus V1 minus V minus divided by R1 plus V output, and we know that the current, use the capacitance law. Yeah, use the differential form of the capacitance law. Current equals to C dV dt. Yeah. Current equals to C dV dt. Okay, current. The Q, remember the basic capacitance law is Q equals to C V, right? And so dQ dt is I, right? Current is I equals to dQ dt. So equals to dCV dt. Since capacitance is usually constant throughout all the time, then this becomes C dV dt. Okay, so this is the capacitance, the differential form of the capacitance law. Remember this from the previous discussion. Okay, from here then C2, the voltage difference that makes this current I that makes the current that flowing through the capacitor is V out. Here this is V out, yeah, minus V minus. Yes, d V out minus V minus dt. C2 times d dt V out minus V minus equals to I minus. So basically this is currents in equals to currents out. Kirchhoff, one of the expression of current, Kirchhoff current law. And since then ideal op-amp assumption is I minus equals to 0, okay, I minus equals to 0, and V output V minus here equal to V plus means equals to 0. So this so this will be equals to 0, and this is equals to 0, and this also equals to 0. Okay, so this becomes what? V1 divided by R1 plus C2 d dt V output equals to 0. Okay, like this. So V1 over R1 equals to minus this move to the right hand side of the equation equals to minus C2 V out dt. Yeah, so based from here, then we can solve the output using integral. Okay, dv out dt will be equals to 1 minus move to the left side. Yeah, become minus 1 R1 C2 dvo dt. So v output becomes integral of minus 1 R1 C2 minus 1 over R1 C2 integral for minus infinity until t v1x dx. So we changed into a different variable from minus infinity until t. Yeah, from here, for any integral, in order that we can calculate the exact result, we need this initial value. So in this case, we are calculating V output. We need to know the V output at 0, at time 0. Okay, clear, yeah, so far. So from this characteristic of circuit, we can understand that this circuit acts or functions as integrator. Why? Because the voltage input here is V1. Yeah, it's being integrated over time, and then the output is the integration result plus the initial result. Now, what if we move the capacitance to the input side and the resistor to the output side, to the feedback, to the output feedback part? Yeah, this one R2 becomes the resistor here now. R2 is connecting the output to the inverting input part of the op-amp. And the capacitance is connected here to the input voltage. We can also add series resistor if we want. And usually there will be series resistor because even wire will have a resistance. So again, using ideal op-amp simplification, then here V plus will be equals to 0, and V minus will be equals to V plus equals to 0, and I minus equal to 0, I plus also equals to 0. Yeah, this is from ideal op-amp simplification. So V plus equals to 0. Yeah, and we use again Kirchhoff current law. The current, we assume that current is entering into this node. Yeah, I1 entering through the C1 into the node, I2 entering through R2 from the V output here to the V minus node. So calculating KCL at V minus node, I1 plus I2 equals to I minus here. So using ideal op-amp assumption that V minus equals to V plus, yeah, equals to 0, I minus equals to 0. So from here we obtain, so this means that this is equals to 0. So from here this becomes this one, yeah, I1 plus V output, I2 equals to V output minus 0, V output minus 0 divided by R2. So this becomes I1, KCL at this becomes I1 plus V out divided by R2 equals to 0. Then we use Kirchhoff voltage law yeah, at this loop. Okay, so this one V1 plus, and this voltage across R1 is I1 times R1 plus the voltage across the C1. We use the integral form of capacitance. Yeah? Again, Q equal to CV. Q is basically integral I dx, right, equals to CV. So V equal to 1 over C integral I dx, yeah, from minus infinity until t. Of course, there is a initial value at the 0. Okay, so this we use to calculate voltage across C1. We use this integral form of the capacitance law. R1 plus using KVL, R1 V1 equals to R1 plus I1 plus 1 over C1 integral I1 dx from minus infinity until t. And there is no voltage here, right? Because V minus equals to V plus, and V plus equals to 0. So this one is 0 plus 0. Okay, there is no other terms here in this KVL. So let's make differentiation from here. Differentiation dV1 dt. Yeah, so if we differentiation on each terms, we need to differentiate. So this becomes dV1 dt. This becomes, we multiply each terms with C1 first. So it becomes C1 dV1 dt, C1 or R1 C1 di1 dt, and this terms becomes I1. Okay, the integral this term we call I1 at t. And then from here, we can calculate, we can replace I1 from this one equals to negative the output over R2. And this is replaced to this, yeah, as well as to this part. Okay. So from here, R1 C1 di1 dt becomes R1 C1 dV out dt, yeah, negative. Then I1 here becomes minus V output over R2. So let's try to calculate it one by one. So this becomes this part, yeah, become R1 C1 d minus VO over R2 plus minus VO over R2 plus C1 equals to C1 dV1 dt. So calculating with R2, so this becomes in calculating with minus also minus with minus R2. So these terms become this term. These terms becomes this term. And this one becomes this one. Okay. Okay. I need to erase now so that you can see the letter. Okay. So, but this all derived from that equation, from the Kirchhoff Current Law and the Kirchhoff Voltage Law. Okay. So if R1 could be set to 0, if for example the R1 is very small, we can then simplify the equation that R1 becomes 0. Yeah, so this becomes 0. The R1 C1 this term becomes 0. So V output will be equal to only minus R2 over minus R2 C1 times dV1 dt. So this is a differentiator circuit, a circuit that differentiates the input signal. Okay. So we have an ideal differentiator if R1 is 0. In reality, R1 there is always R1 in actual circuit. There will be always R1. In practice, an ideal differentiator amplifies electrical noise and does not operate. The resistor introduces filtering action in the R1 resistor. its value is kept as small as possible to approximate a differentiator. Okay, so far any questions regarding integrator and differentiator, the derivation of the formula?
Sir, from V1, the previous one.
Yeah, which one? The differentiator or integrator?
The left below part.
Left below. This one.
No. After this one. Yes, this one. Yeah, how to change from from V1T to the below one.
Okay, yeah, we differentiate. This is from calculus. This is from calculus. So when you have, for example, A equal B, okay, the A dt will be equal to dB dt, right? This is from calculus. So it means when you have this one as well, V1T equal to R1 I1 plus plus 1 over C1 integral I1 x dx, yeah. Then the first part becomes dV1 T dt, right? So the differentiation of the second, the terms in the right hand side becomes since dr1 I1 dt, since R1 is constant, then we can take it out from the differentiation terms, so become R1 di1 dt. Okay, the differentiation of the integral becomes no.
So after differentiate, we times C, yeah?
Yes, that's why. Let me finish first. So this becomes plus 1 over become I1 over C1. So they then multiply all terms with C1, right? So this becomes C1 dV1T dt equals to R1 C1 di1 dt plus I1. So then, yeah, right? This is now already, these terms are equal, right? This, you put this to the right hand side, these two terms you put in the left hand side. Okay. Nikki, clear? Is it Nikki?
Sure. Thank you.
Okay. 1 moment. Okay, so then, okay, about electrical noise. So all electrical signals are corrupted by external uncontrollable and often unmeasurable signals. These undesired signals are referred to as noise. So for example, in the previous example, ideally R1 should be 0, then you would have an ideal differentiator. However, this will amplify electrical noise and does not operate. So the electrical noise comes from the V1. The noise at the V1 will be amplified by the R2C1 component. So we can keep this small by putting that R1, yeah. But also we make it as small as possible, so that then the circuit can still act or approximate as differentiator. But noise are unavoidable, yeah, inevitable. It will always occurs in any electrical circuit. Usually, one major noise source will be from the electrical line, yeah, the 50 hertz from the power line. So that is why we usually later you will learn about filtering the noise. So here, for example, a simple model For a noisy 60 Hertz sinusoid corrupted with 1 microvolt of 1 gigahertz interference. So the actual signal is 60 Hertz signal, yeah, sinusoidal noise, but it has another signal on top of it, which has smaller amplitude with much higher frequency, yeah, 1 gigahertz interference. So when we express that is in a mathematical format, yeah, we put the signal and the noise. We add together the signal and noise. So YT, the overall signal, will be equals to the addition or superposition of the noise which we want to amplify, which we want to process, yeah, sine 120 pi t. So it means this one, the frequency is 60 hertz, yeah, from 2 pi ft. Remember from sinusoidal from physics. So the frequency will be 60 hertz, right? 2 times 60, 120 pi t. Plus this, the noise is 1 microvolt amplitude to 10 to the power of minus 6. Sine 1 gigahertz, so 2 times 1 gigahertz times pi times t. So this becomes the noise. So in this case, the noise to signal ratio is the noise amplitude divided by the signal amplitude, 10 to the power of minus 6 divided by 1, yeah, equals to 10 to the power of minus 6 or 1 micro. The derivative of this signal and the noise, yeah, becomes dy dt equals to 120 pi cosine 120 pi plus, see here, because there is this factor of frequency, yeah? So this becomes cosine, and this factor is derived also, right? This factor will be derived. So 2 giga times 10 to the power of minus 6 becomes 2000 pi cosines 2 times 10 to the power of 9 pi t. So this is why the derivator, the differentiator circuit will amplify the noise, because look here now, I'm sorry, the noise amplitude over the signal amplitude is 2000 pi divided by 120 pi, yeah, it is 16.67. So before the signal, the input signal, before it goes into the differentiator circuit, yeah, the circuit in this slide, the V in, when we assume, for example, it has this 1 microvolt noise, the noise to signal amplitude is 10 to the power of minus 6. But after it is being differentiated by the circuit, then suddenly the noise amplitude increases significantly, yeah, becomes 2000, and the ratio to the noise, ratio of the noise amplitude to the signal amplitude becomes 16.67. So look here, from this much less than 1, right, almost approaching to 0, that's like that, and now much larger than 1. So this is how differentiator amplifies the noise. Yeah, because here you have a noise which has a very high frequency, 2 to the power of 2 times 10 to the power of 9. Okay, when it is being differentiated, this factor is multiplied to the amplitude, so it becomes 2000. Yeah, so this is with differentiator circuit. Okay, now let's learn some problem. Yeah, the application of the RC of M as differentiator and as integrator. So this graph shows the input to ideal differentiator, where R2 is 1 kilo ohm and C1 is 2 microfarad. Calculate, yeah, the V output if the V1 signal looks like this. Yeah, is a sawtooth waveform. So we know that since it is differentiator, if it is ideal differentiator, it means then the output will be the gradient of the input signal. So ideal differentiator, the output equals to, let's look again, yeah, this terms here. So here in ideal differentiator, the R1 equals to 0. Okay, R1 equals to 0. So then the P output will be minus R2 C1 dV1 dt. P output equals to minus R2 C1 dV1 dt. Yeah, from dimensional analysis, ohm is volt per ampere or volt over coulomb per second, or equals to ohm equals to coulomb second per coulomb. Farad is C from the capacitance law, C equals to Q over V, right? Or coulomb over volt. So this equals to coulomb over volt. If we reverse, equals to second, yeah, or ohm times farad. So if we change again, and we can replace here Q with, so ohm times farad becomes then volt times second over Q times Q over volt. So this will cancel each other. So this, the dimension is second. So the dimension of farad or capacitance is basically equal to the dimension of second of time. Okay, so from dimensional point of view. So from here, R2 second times resistor is R2C1 is 1, here is 1 kilo ohm times 2 times 10 to the power of minus 6 farad. Yeah, this is ohm times farad. So the dimension is second, equals to R2C1 equals to 2 times 10 to the power of minus 3 second, or 2 millisecond. Okay. So the gradient here is 10 volt divided by 5 millisecond. Okay, 10 volt divided by 5 millisecond. So from here we put here 10 to divided by 5 millisecond times 2 millisecond. So the result is 20, how much? R2 R2C1 is 2 times 10 to the power minus 3. So if we calculate, let's calculate again. So here the V output will be equals to 2 times 10 to the power of minus 3 in this region, yeah, times 10, 5 times 10 to the power of minus 3. Volt per second, this is second. Yeah, 20 divided by 5 and minus, yeah, because of this minus sign. 20 divided minus 20 divided by 5 equals to minus 4. Yeah, volt. Okay, be careful with the unit. So this is minus 4 volt. So on the between 5 to 10 millisecond, then the gradient here equals to minus, yeah, minus 10 over 5 times 10 to the power of minus 3. Okay, because 10 minus 5 is 5, right? So the V output on this part, yeah, equals to R2C1 equals to negative 2 times 10 to the power of minus 3 times minus 10 over 5 times 10 to the power of minus 3. These cancel each other. This becomes 20 divided by 5, 4 volt. This is 4 volt. Okay. Is it clear enough for everyone? Any questions? It's quite easy, yeah. Now, for an integrator, yeah. So remember the integrator circuit. So the integrator circuit is, you have the source, First is the resistor connected, then the capacitor. Okay. This is integrator. Okay. Input to integrator with R1 equal to 5 kilo ohm and C2 equals to 0.2 microfarad. Okay. The capacitor is initially discharged. This is the voltage. So here we will integrate. Integrate means that if it is flat line like this, constant, so the integration result will be a ramp line. Okay. I have to. Can you still read this? Yeah. If you can see it, I do not need to erase. So the V output T here equals to the, since it is integration, we have to have the initial value. Initial value, then negative 1 over R1 C2 integral 0 until T VI x dx. Okay. So from dimensional analysis, ohm is volt second per column, yeah, volt second per column, and similar to the previous slide. And ohm times farad, here ohm times farad equal to second. Okay, R1 C2, yeah, I guess I still need to erase it. R1 C2 here equals to 1 millisecond, yeah, 1 millisecond. Yeah, from 5 kilo ohm times 0.2 microfarad, yeah, 5 times 0.2 equals to 1, right? Equals to 1 kilo times micro equals to milli, yeah, 1 millisecond, or 10 to the power of minus 3 seconds. So this is R1 C2 here. So from 0 until T until 0.1 second, the V1 T is 20 times 10 to the power of minus 3 then 22. If you already use this one, you don't use millivolt again. So this is volt, yeah, the unit here is volt. Yeah, be careful. If you don't use 10 to the power of minus 3, you just use 20 millivolt. So the result of this integration, integral of 0 to T V1 x dx 20 times 10 to the power of minus 3 times T. Yeah, this is the result. Yeah, so there is a variable T here, a function of T. Yeah, then Y at 0.1 equals to here 2 times 10 to the power of minus 3 times 0.1. So this is the formula. This is the formula for between 0 to 0.1. From 0.1 to 0.2, V1T is negative 20 times 10 to the power minus 3. So the integral of the Y0T, basically then the voltage output is the initial value at 0.1, yeah, which is this one, plus integral from 0.1 until T. The integration of this 2.2 times 10 to the power of minus 3 here, negative 20 times 10 to the power minus 3 here, V1. Yeah, integral of T, and this is the constant. The constant is minus 0.1 from this time, yeah, because this start from minus 0.1 second. So then V output T equals to 1 over R1 C2 Y0T. So this result is then multiplied with this result, 10 to the power of minus 3. So from here, then we obtain from 0 to 0.1, since there is a negative sign here. Okay, so that is why the value here is ramping down. Afterwards, this is ramping up, and here again ramping down again, and then ramping up. Okay. Okay, let's have a break for a while. So there's some application, yeah, where this chapter on capacitance and inductance may find application. So here what you see is the scanning electron micrograph of integrated circuit. So integrated circuit is IC, yeah, or basically many of current electronic appliances or any other computer, smartphone, etc. They have this integrated circuit. The processors are built in integrated circuit, and if you put it under microscope, yeah, it looks something like this, okay, where the circuits are being developed with in a very tiny miniaturized circuitry, yeah, of patterns of metals, and then with transistors inside, resistor, capacitor inside. So if there are two wires, for example, in this integrated circuit that is located next to each other, then there might be some capacitance between the two. Yeah, the capacitance is because the space between the two wires are basically insulating or dielectric material. And there is also capacitance from the wire to the ground of that integrated circuit. And there is a voltage flowing into the wire 1 and wire 2. We can model the crosstalk. Crosstalk means when the current from one wire will interfere to the other wire. Okay. And this is something which usually we don't want in electronics processing. We don't want that the current from one wire will interfere the other wire. Then it will create noise. So this can be modeled, yeah, as capacitance between the two wires, and the current flowing between the wires or through the capacitance C12 here is the I12. The wire itself has a capacitance to the ground, modeled as C1, and the second wire has a capacitance to the ground, modeled as C2. Then we can derive the equation to calculate the I2. Yeah, it's basically using capacitance law, using the differential form of the capacitance law. I12 equals to C12 times dV1. dV1 is this part, yeah, minus dV1 dt minus dV2 dt. Okay, V2 here. So this equals to I2 T, yeah, or basically equals then to C2 times dV2 dt. So from here, then dV2 dt can be derived further as C12 over C12 plus C2 times dV1 dt, yeah, by rearranging the terms. Yeah. So the term dV, where is the, oh, sorry. Oops. Okay. How to stop. So the terms here dV2 dt we will move to this side. Yeah. So then you put the C12 plus C2 in the denominator, and if we found dV2 dt equals to C12 over C12 plus C2 dV1 dt, or V2, yeah, in the, equals to C12 over C12 plus C2 times V1t. So it means we can reduce this crosstalk. Yeah, crosstalk means that the V2 should, if you want to reduce crosstalk, means the V2 should be as minimum as possible. And this can be done by increasing C2. So by increasing C2, this lower term will become higher, that will become larger. So this the whole term here becomes smaller. Otherwise, we reduce C12 and they make this smaller. These terms also become smaller. Or doing both, reducing C12. Yeah, the capacitance between the two wires is made to be smaller, but the capacitance from the wire to the ground is made larger. So here we can use ground wire, yeah, to reduce C12. Okay, because by introducing another wire between the wire 1 and wire 2, yeah, the C12 will be a series of C1G here and C2G. And you know, when capacitors is put in series, the equivalent series capacitor will become smaller, right? So the total C12 here becomes smaller. So by putting another ground wire here, which is this is grounded. Okay, so here I12 equals to C12 dV1 dt, same like here, minus dV2 dt equals to I2 t equals to C2 plus here C2G dV2 dt. Yeah, so here, okay. So since then this becomes larger, the so from here dV2 dt equals to C12 over C12 plus C2 plus C2G dV1 dt. So you have put these additional terms, so this total term becomes smaller. So as a result, then V2T also becomes smaller. This will reduce the crosstalk between this wire 1 and wire 2. Okay. If we want to increase the C2, on the other hand, the C2 is on the part, then we have to put extra wire, extra space in the ground wire. So another example is in memory, yeah, a dynamic random access memory cell, DRAM. So we have here a switch, yeah, where we want to put the value of the voltage. There is a leakage current source here, 50 picoampere. Capacitance of the cell, of the memory cell, with value of 50 femtofarad. This is voltage of the cell. The capacitance out is 450 femtofarad, and then this is to sense the amplifier. Yeah. Here, notice the value of the capacitance. Here is very small, and this is a little bit larger. So here, the current source I leak 50 picoampere represents the charge leakage from the cell capacitor. Yeah. There is always, in reality, when you build the circuit in DRAM, especially at small scale, there will be always this charge leakage. The V cell is larger than 1.5 volt for correct storage of logic 1. Then VC here will be equal can be calculated, yeah, using the integral form of capacitance law. VC equals the initial voltage of the capacitance at 0 time plus 1 over C integral from 0 to T 1 IC x dx. Yeah. So the V cell, if the initial value of the voltage of the cell is 3 volt, yeah, minus the I leak over capacitance of the cell times T, yes, the value of this integration. This should be larger than 1.5 volt in order that a logic one value can be stored correctly. So from here, we obtain that I leak over C cell T should be, because this is minus, should be smaller than should be smaller than 1.5 volt. Then the T for storing that, for what do you call it, for switching on this in order that the correct logic 1 is stored, is calculated like this: 1.5 volt times the cell capacitance here, 50 femtofarad, 50 times 10 to the power of minus 15 divided by the leakage current, 50 times to 10 to the power of minus 12 ampere. Yeah, from here then we obtain so from the TH, the holding time of the switch is to be 1.5 times 10 to the power minus 3 seconds, 1.5 millisecond. So the cell must be refreshed at a frequency higher than 1 over TH. Yeah, something like this. This is the cell at the beginning of the memory read operation. Yeah, this is the capacitor cell, 3 volt. This is the voltage of the input-output circuit. When this is in the beginning, yeah, then when we read the value, read operation is switch is closed. So both capacitor will have the same voltage, must have the same voltage because they are connected, right? They are of the same node. Assuming no loss of charge, the charge before closing must be equal to the charge after closing. So there will be charge flow. The Q before is from the capacitance law, Q equal to C capacitance times the voltage, 1.5 before the switching, 1.5 times 450 femtofarad plus 3 volts times to the 50 femtofarad, times 10 to the minus 15. So this is the before charge. So the voltage after switching, will be the resulting voltage, the same voltage after it is being switched on, times the total capacitance. The new capacitance, since they are in parallel, will be the sum. Yeah, remember capacitor in parallel will be the sum of this capacitance value plus this capacitance value, which is 500 femtofarad. So calculating from here, divided by this value, then we obtain the voltage after will be 1.65 volts at this node. Okay. So even at full charge, the voltage variation is small. Between 1.5 and 1.65. That's why the sensor amplifier are required. After a read operation, the cell must be refreshed. So this is in how it looks like also in IC. If you open an integrated circuit, the integrated circuit is actually in this part. The one that you see, this is if you open the packaging, but the one that you see from the outside is usually only the pad, the electrical pad here. This is usually covered by black coverage. Okay, but the actual IC is very small here. Then it is wire bonded, so that this can be soldered to the PCB. So without this, if you only have this, it will be very difficult to solder any wiring to this manually, to this IC. That's why this is made to spread, to have a larger leg configuration. So this is IC with wire bonds to the outside. This is flip chip mounting, where you have the what do you call it, the pad, electrical pad to the IC located here. This is wire bond, this is flip chip. The goal is to reduce inductance in the wiring and reduce the ground bonds effect. So a simple model can be used to describe the ground bonds. The ground bonds is model like this, where from the VCC there is this inductance from the ball. This ball will act like an inductor because of this ball is a solder ball. Although it is very small, but it still has effect in when we are dealing with integrated circuit. It may have effect. So here, this is, for example, the gate current is shown in this left axis, shown in this darker line, okay, while the ground bonds is shown on the right axis here, in millivolt is as the red part. So here the connection is from the inductance law, L voltage equals to L di dt. The voltage GB here across the ball itself, this one in the solder ball of the flip chip mounting, is from the inductance of the ball times the differentiation of the changes of the current in that ball to the ground. Current flowing through the grid ball. So from here, for example, we have the IDT here is this black one. 40 from this change from 0 to 40 milliampere, and the time required is from here to here. This is about, I think, 60 to 20, yeah, from 20 microsecond to 60 millisecond. So it's 40 microsecond, yeah, 40 microsecond. So this is supposed to be 10 to the power minus 6, yeah, not minus 9. Okay. This is the gradient. So times the L value. The L value is 0.1 nanohenry. If all gates in a chip are connected to a single ground, the current can be quite high and the bounce may be unacceptable. So in order to do that, we need to reduce the inductance. Yeah, use several ground connection balls and allocate a fraction of the gates to each ball, so that then when you are in several grounds, then the inductance will be made smaller, so that the ground bounce voltage will become smaller as well. Power outage right through the circuit. So here we try to design a capacitor that can maintain at least 2.4 volt for at least 1 second. Yeah, when this switch is switched on. Okay, default, this is a 1 milliampere load. So the voltage at the capacitance equals the initial condition. Yeah, so it means like this. So initially it is connected. So the 3 volt will charge the capacitance. Okay, when there is a power outage, this will shut off. Yeah, the power outage is simulated by the switch being turned off. So this function like a energy storage. So then the capacitor must maintain at least 2.4 volt for at least 1 second, so that then this load is not broken when it will be due to this sudden power outages. So calculate the capacitor. So first, Vt equals to 3, the initial voltage, yeah, using the integral integral form of the capacitance law. The initial value 30 negative, and because this Vt after it will start to discharge to this load. Okay, after this is turned off, when it is turned on, the voltage here will charge this capacitor as well as will flow into this 1 milliampere load. When it is turned off, the load will receive current from this capacitors, but the voltage will decrease. Okay, the voltage here is calculated from this formula, integral form of the capacitance law. The initial value is 3 volt minus 1 over C integral I dt. Yeah, to 2.4 volt is the value at least for 1 second. So from 0 to 1, yeah, equals to 3.0 minus 1 over C integral 0 to 1 I dt. So this is design equation that the value is this one is 1 milliampere, right? This is 0.001. Okay, so from here then we can obtain the value C, 1670 microfarad. We have to put at least 1670 microfarad. If we have larger capacitance, then it can maintain the 1 milliampere load at even longer time. The use of double layer capacitor or what are known as supercaps. Yeah. A web search of this topic will indicate that the company America is major supplier double layer capacitor. Yeah, so we can 220 millifarad capacitor related to 3.8 diameter. Yeah, we have to see if there is this value in capacitance, yeah, in the market. If not, then we can use using parallel capacitance to add from smaller capacitance, or using series capacitance in order to reduce from larger capacitance. Another example of design an op-amp circuit to realize this equation. V output equals to 5 times integral. So this is integrator circuit. Yeah. Yeah. So the the C is in the out feedback, yeah, remember, if it is integrator, the C is in the feedback from P output to the negative terminal of the op-amp. The integration is 5 integral from 0 to t V1 tau dt minus 2V2. So this means an adder. Remember adder circuit from the op-amp chapter. So this is an integrator and this is an adder. You can build two cascaded stages of op-amp circuit. The first one is integrator. The second one, this one is an adder. Okay, so this is added with this V2. Yeah, V2. It becomes this one. So the output here calculated from here will be minus V2T R4 over R3. Yeah, this is for the addition from this V2, and then this voltage will be from minus R4 over R2. This is the voltage here is this part, yeah, the one inside the parenthesis, minus 1 R1 minus 1 over R1C integral V1 dt. So this is from the integrator formula that we have derived in the earlier slide. So from here, then this equals to then R4, yeah, this is made together, over R1 over R2, integral V1 dt, minus R4 over R3, V2 dt, this part. Okay. So this will be the integrator part, and this one will be the adder part. So this has to be equals to 2. Yeah, R4 over R3 should be equals to 2. R4 over R1 R2C should be equals to 5. Okay, this is the integrator part, and this is the adder part. Yeah, here should be equals to this term, and this one should be equals to 2. So we have two equations here. Yeah, R4 over R1 R2C equals to 5. R4 over R3 equals to 2. However, we have 5 unknowns. Yeah, R1, R2, R3, R4, and C. Yeah, so we have to select one in order to reduce the unknown. Let's say, for example, 2 microfarad, because it is not too large and it is not too small either. Select R4 to be 20 kilo ohm. Seems to be reasonable value. So then with that way, then R3 we found to be 10 kilo ohm. Yeah. So we are only left now with R1 and R2. And from this choice, we can calculate R1, R2. R1 could be third choice. We choose R1 100 kilo ohm. So then R2 to be 20 kilo ohm. So in design, yeah, we sometimes are given only small number of equation, but there are many unknowns. So we have to choose what is reasonable from the available components in the market, for example, and which is not too large, not too small, and also can be easily found. If supply voltages are 10 volt or less, yeah, this V1, the current will be less than 1 milliampere, which seems to be reasonable. So not too high current. Okay, so when you are making design, it is not like analyzing. You have to optimize, do optimization. Okay. Okay. With that, that will be all for this chapter. And okay. Then I put this turn on your camera. We have a small quiz in the Google Classroom. Okay. And the time is until 11:50. Okay, I just assign it. So at the week 3 part, RC open circuit and transient response on quiz 2 on inductance. So just review your knowledge about inductance. Please do it within 20 minutes. I think it's reasonable for that simple question. So please turn on your camera so that they can monitor you. And submit your answer, scan it clearly. Please use large font, yeah, do not write too small. Alisa especially. And with ballpoint, yeah, not the pencil, yeah, so that the ink can be clearly seen when you scan it. Sometimes it is too blur. Some of your answers are too blurred. So Osama and Michelle, please turn on your